So I just wanted to quickly review self-concordance just to make sure that the whole thing at a high level is clear. The basic idea is to make an analysis of convergence of Newton's method that is, like Newton's method, independent of affine changes of coordinates, right? So that's, and this is to correct this embarrassment that the actual algorithm and the implementation is actually more sophisticated was more sophisticated than the existing mathematical analyses of convergence, right? So, and what you'll recall last time is that it all comes down to this. As you know, the analysis of Newton's method comes down to how big is the third derivative, because that's what it depends on. If third derivative is 0, then Newton's method converges in one step, right? If it's small, that's what tells you it's going to work pretty well or something like that. It basically says how fast does the Hessian change as you move around, right? That's what it is. Okay, the classical analysis just uses that. It uses the most obvious measure of the size of the third derivative. If it was for n equals 1, it would just be f prime 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 absolute value, which is like if someone walks up to the street and says, give me a measure of the size of the third derivative, that should be the first thing you say. Minor problem with that is that is not independent. That is not independent of changes of coordinates. And so if you're given the homework exercise of figure out a way to say that the third derivative is small, that will be independent of an affine change of coordinates. In other words, when you do this, it's gonna lead you to basically comparing the absolute value of the third derivative to the 3/2 power of the second derivative, like period. And you could put another number for 2 there. You could divide it and call it something else, whatever you like. But this is, from that point of view, otherwise this looks like entirely mysterious. Like, where did that come from? But that's all it is, right? What happens when you adopt this way to say that the Hessian varies smoothly or not much is weird stuff happens. So a lot of functions that we actually work with actually satisfy this property, this so-called self-concordant property, right? And I'm not going to go into this, and you can actually look into how you would show this. Not all convex functions, in fact, not all convex functions that we are interested in are self-concordant, but a whole lot are. When you repeat the analysis, an amazing thing comes out. Basically, what comes out is something that I am unable to make fun of, right? Because the way I make fun of a typical, convergence analysis is, here's my prototype convergence analysis. If, and then a long list of things that you could never possibly verify or know. Hold, then, and then it gives a silly conclusion, which is also like weak and pathetic and doesn't really even say anything, right? So that's my model of what I see a convergence analysis looking like. This I can't make fun of because it basically starts by there's nothing unknown in the hypotheses, right? It's just if it's self-concordant, that's it. And we know for a whole bunch of functions that we actually care about it is. And then there are parameters in the analysis. The analysis is very simple, right? It simply looks like this. It says, oh, and by the way, it's measured by lambda, which you'll remember is the gradient times the Hessian inverse times the gradient. It's actually the square root of that or something. That is actually a measure of the gradient, which is independent of an affine change of coordinates, right? So if you have this beautiful algorithm and then the last thing you have in your code is a convergence thing that looks like, norm of the gradient, congratulations, it's now weakly dependent on changes of coordinates, right? So, okay. And it looks the same. It basically says that, if for a while, you are guaranteed that there's a guaranteed decrease of gamma in the function value, right? And then once you're less than this critical value eta for lambda, then in fact you get this quadratic convergence. What's missing are all those crazy things like M and L, which you would not normally know, right? I mean, there would be isolated cases where I would know M and L, right? But mostly you would not, right? So then you get a complexity bound that looks like this. And what's amazing is that is everything here, I mean, oh, one minor, we still have the embarrassment of P star here. We will talk about that. We'll see this will come up maybe next week in interior point methods. We'll take care of that, right? So you can still make fun of it that way, but it's fine, because if I replace P star with any lower bound on P star, then I still get an upper bound on the number of steps. So that's the idea. Okay. Yeah, and if you work this out, this is a sloppy analysis that, Levin and I did. You get something like 375 times the difference. In fact, if you do a more careful analysis, you can get like 11. I think that's the one that Nesterov and Nemirovsky came up with. What's interesting is that actually does kind of give you the behavior, right? This looks like it, maybe there's a better lower bound that has this slope. We could work out what that slope is. But ours is just like almost a straight line going up. And 11 would be, it's only off by a factor of 10. Because it looks like if you take, if you took C equals, I don't know, we could take a look at this, what that slope is, but maybe it's like 2 or something like that. That would probably be a pretty good estimate of it. Okay, so now we'll talk. So just to finish up the discussion of self-concordance, mostly it's used by people to prove convergence of, for example, interior point methods, which will be our next topic, right? So that's what it's usually used for. People have observed that formulations that involve self-concordant functions actually do work better in practice, but I think no one would claim anything strong about that. And for sure, if you were implementing a method and something wasn't self-concordant and it worked well against carefully against a whole bunch of test problems and things like that, no one would worry about it one bit. So just to make sure the whole story on self-concordance is clear. Okay, now we get to something much more important, which is actually the implementation, right? So basically it comes down to forming this Hessian here and the gradient, and then solving this set of equations, which is linear algebra, right? Yeah, and in fact, you could even say, if someone says, what are you doing? You say, I'm minimizing a smooth function. How are you doing it? And you say, well, I'm solving a sequence of quadratic minimization problems. And they go, okay. And you go, quadratic minimization, that's linear algebra, right? So we've reduced minimizing a smooth convex function to minimizing a sequence of, I don't know, some tens or whatever of quadratic minimizations, each of which is actually just linear algebra, right? So, by the way, that means that you can import all the stuff you know about linear algebra with structure and banded and sparse and all that kind of stuff, and it all just slots right in here. Okay. Now, if there's no structure of any kind, that's just going to be like n-cubed flops for an unstructured system, right? If H were like sparse or banded, it's actually going to be a lot faster to solve, right? If you know what you're doing, right? Actually, there's many mistakes people can make. One would be like, forming H and having it be dense. Even if there's zeros all over it, you should kind of check that. But even if there's zeros all over it, it's not going to, some numerical method is not going to exploit that necessarily. Okay, so, all right. Let's see. What you're going to want to do is actually make a map in your head so you know what kind of applications involve a Hessian that has structure, right? So here's a very common one that occurs, is that a function here is going to be it's separable. So it's a function. These are functions of one variable, right? These xi's are the components, right? So it's separable. So it's a separable function plus a function of an affine function of your variables, right? So this is extremely common form that's going to come up. In fact, I guess we're going to see it in just a couple minutes in some applications, right? So here, if you work out what the Hessian of this is, the Hessian of a separable function is diagonal. In fact, that's kind of if and only if, right? If your Hessian is diagonal, then it's a separable function, right? Because it basically means cross derivatives are zero. Like partial xi, partial xj of f is zero, And so that's going to tell you that it looks like this. Okay. Now, the Hessian of this, you can work it out, but it's actually this. It's A transpose. So here we're assuming A is wide. It is going to be A transpose, then H, which is the Hessian of this thing, H0, and then times A, right? So if you look at this long enough, you realize like, oh my God, that is diagonal plus low rank, right? And so once again, once your linear algebra structure center of your brain is all up to speed, that should be blinking, saying you can solve this faster. Okay, and that's correct, right? So if you just ignore that and form an n by n matrix, then call a Cholesky factorization, then each Newton step is going to cost you order n cubed, right? So that's going to be the naive implementation, right? But if you know that it's diagonal plus low rank, you can exploit that, and that might look something like this, right? First, you would do a Cholesky factorization. This is a p cubed operation here. Then you would write out the Newton system as this. You'd actually literally introduce a new variable, w, right? Then you eliminate delta x from it, and you'd end up with this. And you'd recognize these things as Schur complements of various things. And then, you can work out what everything happens here. I'm not going to go into the details of this, but it turns out actually just forming this matrix here is the dominant factor, and that's 2p squared n. This is to be compared to n cubed, right? So if p is like 1/100th of n, then you just saved yourself 10,000x. Everybody following this? Right? So anyway, so this is the kind of thing so when you see things like this, and we could do things like this. What does it mean for the Hessian to be banded? How about that? Just in words. Like what does that mean? Any suggestion? It just means that there are no, I'm going to call, when I take a function, I go partial squared f, partial xi, partial xj. If that's not zero, I'm going to call it an interaction between I and j, right? So what this says is interactions are local. It says that those are zero unless I minus j is really small, like less than half the bandwidth. So that's what it means, right? There's a lot of applications, right? That would be things like control, signal processing. I could go on and on, okay? I mean, these are entire fields would have that structure, okay? And by the way, if the Hessian is banded, how fast can I compute a Newton step? In n, if it's banded. It's just order n, right? Because the factorization is going to be, it's going to actually look exactly like this here. It's going to be this thing, right? So what that says is, I don't know, I mean, just for fun, if I had to solve an optimal control problem with, I don't know, a couple thousand steps by Newton's method, someone want to make a quick guess as to how long that might take? Well, let's say the state dimension is 10 and I don't know, there's like 5 inputs. It doesn't matter. It's some optimal control problem. Yeah, so if you just wrote it out, it might take a second or two. But if you knew what you were doing, it would be sub-millisecond. Okay? So, and this is actually how a lot of things work. So, okay, so this is the key to everything. These are super important things to know. You just have to know these, period, right? So, okay, yeah.
What happened when you introduced the W here, or what was the motivation for that?
This is simply just doing it by, I mean, you could go back and we can call it all sorts of things. W is unelimination, if you like, right? Oh. Yeah, that's one way. Or this is actually just doing, this is exploiting, diagonal plus low rank or whatever. Once you expand it, that's what happens. Yeah. So that's all this is. Okay. Okay. So next up, and this is material that you will need to do this homework thing. Actually, we're probably not going to. I'll say a few things about it, but you actually are definitely going to have to read the book carefully. It's just a couple of pages to get the details of this method. Okay, so let's look at equality constrained minimization. So basic problem is we have a smooth, a twice continuously differentiable convex function here. And we're going to minimize here f subject to ax equals b. And this basically says these optimality conditions are necessary and sufficient, right? It says that when the gradient is in the range of A transpose and you're primal feasible, then that's optimal. And that's if and only if, right? So there's nothing else here. It's just that no qualifications or anything like that. Is assuming f is convex, right? Okay. Okay, so here's a classic example, is quadratic. So here's an equality constrained quadratic minimization problem. Looks like this, right? And the optimality condition now, the Hessian is just p. The gradient is going to be px plus q or something like that. That's the gradient. And then the optimality condition you can write out this way. Okay, so that's what it is, right? This is, anyway, these are the optimality conditions. These are literally these two equations here. The difference is this equation, these are linear actually, right? That's a set of linear equations, that's linear. And if f is quadratic, its gradient is an affine function. And so the KKT conditions become a set of linear equations. And once again, it's just all linear algebra. So that, right, which, good, okay. So when you set it up, it looks like this. This is a very famous matrix. It's actually called the KKT matrix. And it comes up in like pretty much every field I can imagine, right? It comes up it's in mechanics, certainly it's in electrical engineering, it's in lots and lots and lots of fields, right? Okay, so let's see. You can work out this thing is going to be non-singular. It is certainly not positive definite. In fact, it's what people call quasi-semi-definite, right? But so this KKT matrix here is invertible if and only if, roughly speaking, there's nothing, the null space of A does not intersect the null space of P. So if there's a common vector that both satisfies AX equals 0 and PX equals 0, then this thing is singular, right? So that's if and only if. Okay. And there's many, many, many ways to express that. And you probably don't even have to worry about that too much, right? But that's what that is. Okay. So by the way, to evaluate this, to solve that, you could use, we'll see that there's a lot of options you could use. One is you could use an LDL transpose factorization, right, that's a Cholesky factorization but with different signs. And when you do that, that's one perfectly good way. And there's others we will be able to talk about later. Okay. So the first thing, I don't know if you remember, but basically like in week 2, I pointed out you could actually eliminate equality constraints. You just don't need them, right? They don't actually bring any, like we can just get rid of them arbitrarily, pull them back. It doesn't make any difference. And the way you do that is if you have an equality constraint AX equals B, then you parameterize it as the image of an affine function, right? And that requires you to find a particular solution, say X hat. And then you find a matrix F whose range is the null space of A, right? So that's actually all, that's actually all you need. And there's very simple ways to do that. You could do a QR factorization on A transpose or something. This is just linear algebra at that point. Okay, and that's the idea. Then what you do, it says that this is a parameter, you'd call this a free parameter parameterization of this set, which is affine set, which is described by constraints, right? So that's how you describe that. Okay. Then you just solve this problem, right? Because everything that satisfies AX equals B has exactly this form. And now this thing is that's an unconstrained problem with some variable Z. I could do all sorts of things. I could actually, once I know, by the way, Z star, I can reconstruct X star and even nu star as well, right? But by these methods, right? So, okay, so that's an equivalent problem. And this this just works by Newton's method, right? So we just use Newton's method to solve that. And I'll just give you a quick example. Here's a famous problem. It's like, it's resource allocation, right? So x1 up to xn are a bunch of resources that I am going to, those are the resources allocated to agents 1 through n. That's what the xi's are. B is my total budget. That's how much of my resource I'm going to allocate across years. You can make the x's non-negative. It wouldn't make any difference, right? And then I have a cost function for each of my agents, like f1 of x1 is the cost if I allocate x1 to agent 1, right? So that's how that works. So this is sort of the total cost. And you have this equality constraint, right? One way to eliminate it, I mean, this is easy, is what you do is you leave x1 through xn minus 1 alone, right? They're going to be, we just keep them. But we write xn as b minus them. We just remove this. Then you put a function that looks like this. So here my z's are really just x1 through xn minus 1. When I multiply by f, this you can check that this thing is a basis. I mean, by construction, this works, right? You can check that the range of this matrix is exactly the null space of this matrix. That matrix is just a 1's vector transpose, right? So that's what that is in AX equals B. Okay, so then you end up with this reduced problem. There you go. Oh, any comments about that function? Anything you like about it? Can we all visualize its Hessian, please? What is the Hessian of this function? What is it?
Arrow?
It's what?
An arrow?
You know, it's not arrow. It's very close. If you were to do one elimination, it would be arrow, but it's very close to arrow. It's not arrow. This is dense. It's completely dense. But what is it? What's the Hessian of this part? Diagonal. Okay. How about the Hessian of this? What is it? It's rank 1, right? You can just check, right? It's going to be actually it's literally the matrix of 1's. It's actually 1's transpose times a number, right? That's what it is, right? So yeah, I realize you're just seeing this all now, but this is the important thing. This is what you need to do, right? Is to be able to actually be able to recognize these things in the wild, right? Is you're going to want to be able to see things like this. So yeah, so this is diagonal plus rank 1. So when you see this, you should be able to look at that and say to someone, I can solve that in linear time. And they would say, wow, how do you do that? I thought Newton, I'm using like, SGD because it's too big or I don't blah, blah, blah. And you're like, no. They go, but I have a million variables. And you're like, too bad. I can do it on my phone. Okay? Everyone following this? So these are extremely good things to know about, right? So, because I don't know, every day there's people who don't know these things making the wrong conclusion, arriving somewhere and saying, oh, I tried like NumPy and it was too slow or something. Yes?
The point of the F matrix, because I don't see it in the reduced problem. So
it is here. What I've written here, this is literally, it's the original F of then capital F Z plus X hat. So I'm just writing it out in its more natural form, but that's exactly what it is, right? In fact, you can sort of see that, right? Here. With this one, the F is an I stacked on top of a minus 1's. Here's the minus 1's, and here's like the I. That's an n by 1 by n minus 1 I. N minus 1 by n minus 1, yeah. Okay, cool. This is, okay. So the Newton step, you can also directly get, the Newton step from the KKT system, not by doing this reduction, right? And so to do that, you form this system. And this is just literally, this is the definition of the Newton step. And it's lots of cool interpretations of it. One is this, you'd say, well, I want to minimize this smooth function subject to AX equals B. And someone says, cool, please take your function f and make a second order Taylor expansion, which is going to be a constant plus a linear term plus a quadratic, convex quadratic. And then you say you want to minimize that subject to AX equals B. But that matches something you have a solver for. It's called linear out. It's called, you form a KKT system and solve it, right? So that's one interpretation of what this is. Another interpretation is pretty cool, is that the so-called, this Newton step here actually comes from linearizing the optimality conditions. So one of the optimality conditions is already linear, right? This is already, so no linearization is needed here. It's already just a set of linear equations, right? This one is going to be, this one is going to have to be approximated, right? So we'll approximate this by its its first order expansion of the gradient, which is of course related to the second order expansion of the function, and we get something like this, right? So you can say that the Newton step are something like this. It's a delta x and a w, for which if you were to take that step and if your original function was quadratic, that would actually just be the optimal solution, right? That would just be the solution. Everybody got this? So this is the Newton step. Okay. The Newton decrement, we saw this before in the unconstrained case, right? And it turns out you can write it lots of different ways, but it is the norm of the Newton step in the metric given by the Hessian. But maybe a better way is this. It basically says it's the 1/2 lambda squared is actually the predicted decrease in f if you took the Newton step and if the function were quadratic, right? So that it was exact, right? So it's actually, as a practical matter, a very good approximation of how far from suboptimal you are, right? Okay, so this is the Newton decrement. And now we get Newton's method. So here it is. You start with something that's feasible. So ax equals b and x is in the domain. And you compute the Newton step and decrement. You stop. Otherwise, you do a line search by backtracking and then you update. Actually, you might ask, how is this algorithm different from Newton's method without equality constraints? Right? Reasonable question. The answer is it's not. They're identical. It's just the same. What's different is, for example, when you compute the Newton step, if you have equality constraints, you're actually solving that KKT system, not just with the Hessian. But it's just exactly the same, right? So that's the idea. And this is a so-called feasible descent method. What happens is xk, of course, x0 is feasible because you have to start it with ax, something that satisfies ax equals b and it's in the domain. You're always in the domain, always have ax equals b. And in fact, not only that, but the function value goes down. And this algorithm is affine invariant. So if you change coordinates or rescale the variables, at least to first, it doesn't make any difference at all. You get exactly the same number iterates, the same iterates. Okay, so that's Newton's method. What's cool is that we don't need no more analysis of it. And the reason is this. It turns out if you apply Newton's method to where you eliminate the equality constraints like this, if you work out what it is, it turns out it is identical to just running Newton's method. Right. So it's actually just exactly the same thing, right? Everything is the same. Like absolutely, the iterates are identical, the primal iterates, the dual iterates, the lambda is the same. So it basically, that means we can actually pull in the proof of convergence from whatever last lecture, right? So that's all we need. Okay, so we don't ever have to. We're not going to talk about like does it converge and all that kind of. The answer is yeah, it does. And we'll see. Then you'd say, well, what would be the difference between these two, right? And this gets you into the usual thing, right? If you, in this case, you say, well, I'm eliminating, and so I'm solving let's say you have 1,000 variables and 100 constraints, right? Then someone would say, what are you doing? You'd say, well, I've eliminated the equality constraints, so I'm solving a problem with 900 variables. Everybody following this? And you'd say, well, what are you doing? And you go, yeah, I'm solving a problem with 1,100 variables. Everybody got this? Right? So that's if you solve the KKT system, right? Because it's a 1,000 by 1,000 blocks stacked on top of a 100 by 1,000 A matrix. Okay? So someone else would look at them and say, but wait a minute, last time I checked, 1,100 cubed is bigger than 900 cubed. And you'd say, it is, you're right. But what we'll find is actually that it's almost always better to just solve to solve the bigger system, right? So this is the other thing. If someone comes up to you, I mean, the matrices have no structure at all. Obviously, you'd prefer to solve a smaller system of equations. But when there's structure, this is, generally speaking, completely false, right? So, and it's not intuitive. So, okay. Okay. Aha. So now we're getting to something which is related to something you'll do in your homework, is the so-called infeasible start Newton method, right? And what it does is it's actually a simple extension. Before we assumed that x was feasible, and so ax minus b was 0, right? Then this just says, well, suppose you're not 0. What is the Newton step, right? And it's defined by this here. And you can write out all sorts of cool things about it, right? It's linearizing if you write the residual as, well, two things here. We can have if you write out this thing, if ax equals b, and this residual should be about 0, you get these things. And the solution of this is called the infeasible Newton step, right? And so this is basically 95% of what people actually use, right? So, or actually, since you've been solving lots of problems, it's what ecos and all sorts of other things have been using on your behalf, right? You didn't know it, but that's what it was doing, okay? You'll know all the details by maybe next lecture or something like that. Okay, so this is the infeasible start Newton method. And there's some very interesting things about it. First, if you take a step of size 1, you will, then the equality constraints will hold. You will be feasible if you take a step of 1, and you'll always be feasible thereafter. Because once you take a step of 1, it's feasible. Once x is feasible, this is 0, and it actually becomes, except for the line search and the stopping criterion, it's basically identical to just Newton's method with equality constraints. That's why it's called infeasible start. We'll see why you might want to use this. There's some very good reasons I'll get to in a minute. Yeah.
So you said that, like, once you take a step of 1, it becomes the same except for the stopping criterion and stuff like that. Like, would you in practice take a step of 1 and then change back to the original criteria?
No, you may not be allowed to take a step of 1, and it's a good. So actually, what I'm about to say is highly relevant for the homework you're going to do in the next couple of days. You may not be allowed. You may not be able to take because, for example, a step of 1 might take you outside the domain of f. Okay, then so you may not. That's one reason. We'll look at the line search for the infeasible start Newton method. Actually works with instead of working with the function value, it actually works with the norm of the residual, right? So it actually works with the norm of the residual. So you look at, I'll call it z, right? You would look at this. Z is going to be like x stacked on top of nu, right? So, and in fact, people call z the primal dual variable because it's basically top of it is the primal variable and the bottom is the dual variable, right? So, okay. So, and I think, let's see. So here's the infeasible start Newton method. You will implement this, so I would strongly recommend listening. You also want to look at the book and stuff like that to read a couple pages about this. So here, the initial point does not have to satisfy ax equals b, period. Does not have to. It must be in the domain of your function, right? So if your function was something like minus the sum of the logs of the components, can someone want to suggest a reasonable starting point? What's the first? If I say, give me a function, give me a number that's in the domain of negative log x, just what's the first one that comes to your head? There you go, 1. Good, I like it. Okay. The truth is, you could have said any positive number, and I couldn't have said anything about it. So, okay. So, okay. So that's the initialization. So you compute the primal and dual Newton steps. The backtracking search is actually on the norm of the residual, right? And we have to look at this equation we have to look at this sort of pseudocode pretty carefully here. This says that if this norm does not go down by some amount like that, right, then you have to multiply t by beta. Beta is this number, like typically it's a half or something like that. Actually, people use all sorts of things, but they would never, you could use a half, a quarter. Some people use 0.1. Doesn't matter, it turns out. Okay, very important thing here is one of the requirements is that x plus tx Newton has to be in the domain of f, right? So let's suppose the domain of f was r plus plus to the n. That's what it's going to be for your homework problem, right? You calculate a Newton step, okay? Here's what you do. You don't just take x plus t delta x and then evaluate the gradient in Hessian, right? Because if x is outside the domain, so an entry of x is negative, for example, or 0, then the gradient, actually you're really going to be messed up, especially if you had formulas like the gradient is 1 over x minus 1 over x and the Hessian is 1 over x squared. Unfortunately, those things will evaluate correctly to a number, even if x is negative. Everybody following this? But nothing good is going to happen after that. Absolutely nothing good is going to happen. Your algorithm will not work. It's complete. Nothing will happen, right? So that's why I almost wish that they had in math libraries, you could simply say the domain of, actually, no, you'll evaluate, if you were to evaluate, so these are interesting because you actually don't evaluate f anywhere here. But if you did, you'd know you're in trouble because you'd get an error saying, hey, you're trying to evaluate the log of a negative number, right? Or 0. And that's not going to go very well unless you have a complex library or something like that, right? Okay. So the way to do this then, so what that means is if this is not in the domain, this isn't even defined. This just means it's infinity. So you would take a t, check if x plus t delta x is positive. If it is not positive, don't evaluate this, right? Just times t times equals beta. And you keep doing that until you're actually in the domain, which means it's positive, then you can evaluate this. Okay, so I don't know if that was clear, but maybe to those working on this already, it is. So, okay, so I think that was enough of a hint, but it's an important one, right? So, okay. So this is it. And the basic idea of this is that the directional derivative is in fact also equal to minus the norm of the residual. So what that says is if you're doing a line search, it's pretty cool. It looks like this. This is t. This is the norm. I'm going to plot here the norm of the residual, right? So at t equals 0, it's at your current point. And what it says is that the slope of this curve is exactly minus 1. Right? So if you're going to make that step, backtracking or Armijo step or whatever you call it, it's going to look like this. It's just going to look like that, right? And so you will degrade this by alpha, and you will take the first time you get something that is below that curve, and you absolutely have to, because if t is small enough, it's got to happen. So, okay. You actually did this, even though yours isn't quite. There's some questions as to whether or not it's working.
I think I made this error.
Okay. Well, sorry. That's what you get for doing it. Sorry. We should have done. Yeah. Anyway, that's the timing. That's right. That's it's a good experience. It's a good life experience to have. Everybody should actually at once in their life write a Newton thing or something like that where they were too cavalier about domains and nothing, and it was bad. Right. So, okay. All right. So, you'll be implementing this for the homework. Okay. Let's talk about how you solve the KKT system, right? Well, one obvious thing, which is, by the way, not bad at all, is actually just doing LDL transpose factorization. So here's good news about LDL transpose factorization is if you use a good sparse package, then I'm assuming H and A are sparse, then it's actually going to exploit it's going to exploit a lot of structure there, right? More even than you know about, right? So, so you could do this for a control problem, signal process, all sorts of stuff. You could just do this, right? You can do elimination. This is often done if H is diagonal, right? So if the Hessian is diagonal, like for example, if the function is separable, right? It's separable, but they're coupled by the equality constraints, right? then H will be diagonal. And in that point, that's tempting enough for you to do elimination on it, right? So you would eliminate, because we know the inverse. H could be banded, same story, right? So, I mean, here's an example of a banded one. Optimal control with a constraint that, some constraints that couple states far apart. For example, you're making a tour. You say, make me a little drone tour. And it's got to start and end at the same place, right? Well, okay, so the way when I hear that, when I hear optimal control, I visualize immediately a banded system. I know immediately the banded system is going to drop down somewhere deep in the linear algebra. I'm going to solve a banded system, can do that super fast. But when I say something like, you have to be back at the same place, that actually couples like the beginning position and the final position. And that's actually one of these, that's going to be an equality constraint that breaks the bandedness, right? But I'll also know that I can do that super fast. So in other words, that's just a non-problem. Okay. All right. So to eliminate here, H inverse, and usually this is done when H is like, something like diagonal. So you would just do a block elimination here, and you'd end up with something looking like that, right? So you would form this matrix, then factorize it, then solve, right? And H inverse you shouldn't even worry about because it's diagonal, so it's kind of a silly thing, right? And then you'd end up with something like that, right? So this is once you form, this would allow you to solve for W. Once you solve for W, you solve for V over here, right? And that's cheap. Well, it's silly. H is diagonal, so that would be that's the idea. Okay. All right. Okay, so we're going to look at, so actually what's weird about all these things is that they're all kind of the same, all these different, so now you have lots of different methods, right? By the way, this is shockingly close to what you will be solving in your homework. So again, you might want to listen up as to how all this works, right? So we now have all sorts of different ways. So you could say, yeah, I could solve that. It's smooth problem, and you could say, oh, I could solve the dual here, and in this case, you could actually you could reconstruct the solution of the primal from the dual. It's not always true, but it is if the objective is strictly convex, which it is here, right? So you could say, oh, you could do this. All right, so let's just do the simple thing. Actually, here's what's interesting. They all have different initialization requirements. And actually, that's actually what's going to actually be you're going to see that all these methods are going to turn out to be essentially the same. They're not the same, but in spirit, the work you do per iteration, if you know what you're doing, is the same. So there's just no difference between any of them. So except the initialization. So if we just do Newton method with equality constraints, that says someone has got to come up with an x that is strictly positive and satisfies ax equals b. If these are just general A's, if this is just a general A and B, how would you find such an X? I guess you'd have to solve, in general, you'd have to solve an LP, right, to do that. So, and this is bad because this is, maybe simpler than an LP, and it's a general rule that you should not have a subroutine that's more complicated than just solving the problem itself, right? So on the other hand, sometimes it is easy to come up with even though there's an equality constraint, sometimes this is easy to do. How about resource allocation? Where here's the constraint. Ready? The sum of the x's is equal, I'm going to make my budget, b. There you go. Sum of the x's is equal to b. Can someone suggest, and suppose that all of the, suppose all of the functions that I want to minimize, or actually you'd call this log utility, which is actually widely used. So this would be log utility allocation of resources or something like that. Someone got a suggestion for, can you think of a positive vector so b is a scalar for us now, right? It's sum xi equals b, that's the budget. So I'm deciding how much IO bandwidth or something like that a bunch of processes get, okay? So what's an initial resource allocation? What?
B divided by n.
Perfect, uniform, yeah, you just do each xi is b over n, and you put a comment in the code that says we initialize with uniform allocation. Done. So then you can do this. Okay. All right. So here's what happens if you run this. I think this is just run from several different initial conditions. And you see your classic Newton thing. This is what you're looking for, right? This is a log plot, and this is linear. This is a semi-log plot, and you're looking for this acceleration, right? That's when you declare success. That's Newton's. That's how you know you actually have an implementation of Newton's method. Okay. So okay, and you have that. Okay, that's one. We could actually apply Newton's method to the dual, right? And let's actually see. I think, I can't remember, let's see, did I say what I did say what the numbers were. Aha, okay. So here I said that there's 100 equality constraints and 500 variables, right? So in this problem, yeah, we have basically 500 variables, right? But then someone says, oh, no, I learned about this dual. It's really awesome. Plus it sounds fancy, and so you can impress your friends if they're gullible or whatever. And you can say, oh, no, to solve that resource allocation, I'm going to solve the dual resource allocation. And if you say it the right way, it sounds really sophisticated. And then someone you could even then say things like, actually what I'm doing, mine is a price discovery method, because the dual variables are in fact precisely, in a resource allocation, they are precisely the marginal utilities, right, of the thing. So you'd say, I'm solving the dual problem, and you could blabber on and on. And you'd say, also, plus I only have 100 variables. Whoever was solving the Newton thing, they had 500. And last time I checked, 100 is smaller than 500. So should be, I should be a factor of 5 cubed better. I should be 100x faster. Everybody following this? This is what someone might say, and actually people say this all the time, is completely wrong, of course, right? So, okay, so we'll solve this method, and then you get down and you say, oh, look, you started from a couple of different things. Oh, by the way, this requires, you have to have something feasible for the dual, and that's basically, I have to find a vector with A transpose nu positive. Once again, how do you find well, it depends. In some cases, it's easy. In the simple resource allocation, it's easy. In others, it's not. Okay, everybody following this? Then they'd say, oh, look, I had 9 iterations. That was fewer than you did with Newton's method. Newton's method took 14 iterations, plus you have 500 variables. I have 100 variables, and I did 9. Everybody following this? So I have heard people say this to each other, or put this in slides. It turns out it's all so wrong and so stupid, it's not even funny. So, okay, so we'll get to that. That's a fun part in the end. Then you'd say, well, there's the infeasible start Newton method. This is the only one that has a extremely simple initialization, right? You don't have to satisfy AX equals B. You only have to satisfy that you're in the domain of F. F is the sum of negative logs. The domain is R++ to the n. So you initialize with 1s or your favorite other positive vector, and you're done. Okay? And you'd say, look, here's what it is. And they'd say, oh, you're doing 22 steps. Anyway, this is all just silly, right? So, okay. Let's look a little bit more closely at what happens. Oh, by the way, these methods would be wildly different if you used naive linear algebra. If you used naive numerical linear algebra, they would be wild. If you actually formed a KKT matrix or whatever for the full thing and solved it, this would be different. So but if you actually do the analysis to figure out, assuming you actually know how to use linear algebra, then it turns out, well, it's not shocking. They're all actually identical in complexity. We'll see how that works. So to use Newton's method, you use block elimination on this, and you would end up solving something that looks like A times a diagonal matrix times A transpose. That's what you'd form and solve that system. Okay? Okay. Notice that this is the smaller one. That's the 100 by 100 linear system, right? If you wanted to do the dual, you'd actually have to work out what is the Hessian of the dual objective, right? And it turns out it's going to be identical. You're going to solve something that looks like A times a diagonal matrix, positive matrix times A transpose times delta nu. And this is just the detail of what it is. Okay. So once again, you would solve a 100 by 100 set of linear equations. Okay. If you use block elimination, you end up with this. Oh, hey, wait a minute. That's identical to this. The only thing different is that this is 0 because you're assuming x is feasible. And down here we actually are putting in the residual, right? So this need not be 0. If you're not yet feasible, then b minus ax is not 0, right? And this is going to actually reduce to solving this exactly the same system, but with a different right-hand side, right? That's the difference. So the conclusion is that basically in all three of these methods that look wildly different, and someone could try to argue they were wildly different, right? It's all the same, right? By the way, this is the same generally for duality, right? That if someone says, oh, especially for Newton's method and things like that, they say, oh, no, I'm going to use this to solve the dual or something. For methods like this, they're no different if you use smart linear algebra. If you use naive linear algebra, they're very different. There are reasons to solve a dual instead of a primal, but it's much more advanced. It has to do with if you want a distributed method or something like that, then it can start making a difference. But for a lot of these, there's no difference at all. Okay. Let's look at, this is actually a real and cool example. So let me just show you what it is. It's I guess, flow utility maximization, right? So looks like this. I have a graph, right? So I have some vertices, right? And I'll make it directed, right? So here's my graph. I mean, this doesn't matter, right? But I'm just going to draw a picture of it like this. There you go. Okay, there's my graph. And then what I imagine is that each xi is going to represent a flow on an edge. So there's a flow here. By the way, x can be negative. As those of you in EE would know, this is called the reference direction. X negative says simply that the flow of whatever it really is, like, for example, electricity or current, charge, I should say. It means if it's negative, it means it goes in the opposite direction of what's called the reference direction. Everybody got this, right? So, and this comes up in a lot of things. AX equals B is actually, AX equals 0 says that you have flow conservation if A is the incidence matrix, right? That would be flow conservation. And in fact, you call an x with AX equals 0, that's called a circulation, right? Because it's something where at each node you have conservation, right? And so an x that satisfies that is called a circulation, because here's an example of a circulation. I have a flow of 1, 1, 1, 1. It's a flow in a circle here, which would be, that would be a circulation. When you have B, what it corresponds to is that you actually have, someone is injecting at each node B. So, and again, this could either be injecting or pulling stuff out. Depends on what it is, right? So this is what a network would look like for that. Here, I'll put another edge here just for fun. So this is my network, right? And this would have lots of examples. Oh, some people call it a single commodity flow problem, right? Single commodity means there's a single commodity, which is whatever is moving across here. It could be charge in an electrical circuit. This could be a power grid where we are not taking into account like transmission losses, right? So if someone is pumping power in, that's a generator. If they're pulling it off, that is a load, okay? And then this is the power flows on all these transmission lines, right? This is neglecting losses in the transmission line, which is actually not a bad thing. It's a perfectly good model for some of this. Okay, so this is what this. But this could be like lots of other stuff, right? This could be flows of money in a banking system. Could be all sorts of stuff, right? Flow of mass or something like that. Movement of a drug from different compartments in a person, right? That's another one, but okay. All right, so this is network flow optimization. Okay, so the matrix A is like super duper sparse because actually each column has at most, it has exactly 2 non-zeros. It's got a +1 and a -1, right? Because each column corresponds to one edge here, and one edge goes between 2 vertices, so there's exactly 2 non-zeros, right? So A is this, I guess, A tilde. This is because we're going to reduce it in a minute. So A tilde is going to be, the A tilde is the so-called node incidence matrix. That's not full rank. So you'd like remove one row and refer to, by the way, you do that and you refer to one of the nodes as ground. Now I'm speaking EE dialect, but that's what you do, right? So, okay. Let's see. How do I know that this is not full rank, right? I mean, how do I know that if I write a matrix that looks like this, right? Here, right? If I make a matrix that looks like that, and how do I know it's not full rank?
It becomes a reduced form.
Yeah. So if you just add up all the rows, you get 0, right? So that means like 1 transpose A is 0, right? And one's vector is not 0, so that means it's not full rank, right? So anyway, I won't go into the details. This is just very good stuff to have seen. Actually, how many people have seen stuff like this in some class somewhere? So okay, good. What context?
Flux balance.
Oh, flux balance in biology. Okay,
Yeah.
good. Yeah. Okay, you too.
Yeah. Linear programming class.
Yeah. Okay. Oh, linear program. Okay. Good enough. And flux balance. So, okay. All right. So let's look at the KKT system for this specific problem. Oh, so you're looking at this and you'd say, I don't know, how easy. Okay, California grid has about 3,100 X. No, it's about 6,000. Come to think of it. Sorry, there's about 3,100 generators. And there's about maybe 6,000 transmission lines roughly in California, right? So the question would be, that's actually that problem doesn't scare me, because even if you were really dumb and just did it with dense and everything, it would still be just fine, right? But if I took I don't know, if I took the U.S. Western grid, then it would not be the case anymore, right? We would start getting 50,000, 100,000. So we'd be getting some big problems there. Okay, but when you see this, you should lots of signs should be blinking. Number one, your objective is diagonal, right? So, sorry, the Hessian of your objective is separable, which means your Hessian is diagonal. So that should the first time you see this, you should just say, okay, I'm primed. I'm ready to do some actual linear algebra here. Then you see AX equals B, and you say, what is that? And you say, that's this node incidence matrix. Every column has exactly 2 non-zero entries. Then your sparsity part of your brain should be now blinking, right? And so at this point, you should actually, depending on, I don't know, you could say to whoever asked you to solve this problem, you could say, well, we're going to be able to solve that shockingly efficiently. And they'd say, yeah, but I have 1 million X's and 10 million, I have 1 million nodes and in my power network, and I have 10 million edges. Really? And you go, yeah. They'll say, are you going to use a gradient method? And you're like, no, dude, we're going full Newton on this, right? And they're like, how could you do? You see what I'm saying, right? There's still people stuck in this mindset. Actually, I'd say the vast majority would not know this, right? So anyway, and you'd say, yeah. They'd say, well, how can you do that? You can't even form the Hessian. And you're right. You'd say, yeah, you're right. I'm not going to form the Hessian. I'm going to solve a KKT system. I'm going to exploit the structure, and I'll be able to do it fast. And that's how. Okay. So here it is. That's our diagonal. That's our diagonal part of the Hessian. We'll do some elimination here, and you'll end up computing, forming this matrix here. By the way, this matrix is, if you've heard of it, it's a Laplacian matrix, right? So in circuits, this would be literally the conductance matrix. Again, that's how you'd say it in EE. But in other fields, it's got other names, right? So this is a conductance matrix. Or a Laplacian. Laplacian means the diagonals are positive, the off diagonals are non-positive, and the sum of each row is going to be 0. Okay? That's if we don't do the reduced one, but that's fine. Actually, if we do the reduced one, it's fine too. Right? So everybody got that? So this is, yeah. By the way, this thing here, solving so-called Laplacian equations like this, that's like a whole sub-industry, mostly theoretical computer science, right? So, so this, you could, if you type that into Google, you'll find lots of stuff. Mostly, to be perfectly bluntly honest about it, completely and utterly useless. There are very good methods to do it that are not those, right? So, okay. Okay, so let's see. You can even say this thing, this Laplacian matrix, is actually, we know the sparsity pattern of it immediately, which is really cool. It's basically this. It's basically nodes by nodes. So if I had, a million nodes, this would be a million by million matrix. But what it says is that nodes I and j, it's only if they're connected by an arc would it be true that this matrix here, the Schur complement, is going to have a non-zero. Okay? So if I told you my original power network had 10 million nodes, a million nodes, 10 million edges, right? And suppose I told you that there weren't weird things where there's not one thing with 50,000 edges adjacent to it, right? If I said, look, the degree of a node varies between like 2 and 50, right? Then that tells you that the number of non-zeros in this matrix per row is between 10 and 50. Everybody following this? And that's going to qualify as a sparse matrix. Okay? Everybody following this? Right? So what it means is that you can solve network flow optimization problems for, I don't know, very large problems if you want, and if you know how to do it. Okay. So, all right. Did all that make sense? Yeah. Okay. We'll look at something. This is a little bit more esoteric, but just to show you that the ideas. I mean, you just use these ideas whenever you can, right? So on any specific problem, you work out what they are. So here's one where our variable is actually a matrix capital X, right? Which is, it's n by n, my matrix, right? So one option for this would be to string out all the entries of X. X is symmetric, so there would be n plus 1 over 2 entries if I vectorized X, right? Because that's the number of distinct elements in a symmetric matrix, right? So then I could compute the Hessian, which would be an n plus 1 over 2 by n plus 1 over 2 matrix. Everybody following this? Okay, so that's got n to the 4th entries in it, right? Then if I just naively, then I stack A on top of it, right? I'd form a KKT system, right? Anyway, I'd end up with a giant matrix that was basically n to the 4th by n to the 4th. Everybody following this? So, something n equals 200 is going to be a kind of a showstopper or something like that, right? Because it's just going to be too big, right? But it would, in theory, it would work. You could actually do this, run this, and then reassemble X into a matrix and all that. So it turns out we'll do a lot better than that. By the way, each Newton step there would cost you n to the 6th. Here's why. The number of variables is really n squared, right? Because I used n to say X is n by n. It's n squared over 2, roughly, right? Then if I form this matrix, my storage is going to be n to the 4th, and the computation per iteration is going to be what would normally be, it's the size of the matrix cubed, but if that's n squared, that's going to be n to the 6th. Everybody following this? So, okay, that would be bad. By the way, you might ask, who uses this kind of stuff? This comes up. Oh, I could give an interpretation of that in probability and stochastic processes. I could this in control. Things like this come up all the time. But it comes up. So things like this, people actually do solve. Okay, now we'll do it the right way. So the right way is to write down the optimality conditions here for this problem. And the truth is, you don't want to calculate the Hessian of the determinant of the inverse of a matrix, right? I mean, or I can tell you what it is, but you do not want to write it out, right? Actually, you can't. You can write it out as an abstract linear operator pretty easily. So, but let's look how this works. So the conditions are that, I mean, it's got to be positive definite, otherwise this makes no sense, right? And then the gradient of this I'm not too afraid of, because that's minus x inverse, right? So that's the gradient. The Hessian is not too bad either. Okay, so I write this out like this. And so these are the equations I really want to solve. And in fact, what the Newton method is doing is it's actually just linearizing this. These are linear. They don't need to be linearized, right? These are not linear because of this, and you just linearize that. When you linearize this, you end up with that. That's the derivative of the inverse of a matrix. And it makes sense, right? Because minus 1 over x, if you take the derivative of that, is 1 over x squared. That's for scalars. For matrices, then the only question is, how do you say, x, 1 over x squared in matrices, right? And there weren't too many ways, but this is the way to do it, okay? So you get that. So we have to solve these equations here. And remember, we're going to try to find this matrix delta x, and we're going to try to find these dual variables wj, right? Okay, so this is the idea, and you have a bunch of variables. You have basically n squared variables, right? And all we're doing is this is just block elimination, but doing it manually for this particular problem. So what you do is you eliminate delta x from the first equation by multiplying. You go back over here. You multiply this equation by x on the left and the right. Okay? And you'll get like an x and an x and x over here. This will become x, and this will become delta x over here. And you end up with this equation here. Then you substitute that in the second equation, and you get this system of equations here. And that's a dense, positive, definite system of linear equations, which you then solve. But if you work out the whole thing, what's going to happen is you have various things here. P is small, right? But the main thing that's going to cost you is going to be the piece like p squared, n squared, or pn cubed, this kind of thing. And notice that the entire thing is now quadratic in n, whereas the super naive method was the 6th power in n, right? So that's the same as going from sort of n cubed to n, going from cubic to linear. And that's what's happened here, once again. Except the number of variables is like n squared over 2, so that's the same thing. It went from n to the 6th to n squared. That's a big difference, right? Okay, so, and, oh, yes, you didn't know it, but this has been done on your behalf. Anytime you ever solved an SDP, this is what was going on in the solver, right? You don't need to know it, but which is kind of the point. Okay, so this finishes up the equality constrained minimization. You will do a homework problem on it. I was going to say it's worthwhile, spend some time on it, but I would hope if at some point, if you've been working on it for 2-3 hours and still debugging, you should have the sense to just step away from the keyboard, right? Hold your hands up where other people can see it, and then just walk away. I just say this because I've even had people come and say, I've been working on this for hours. We'll look at the code together, and I can't figure out what's wrong. So this is just slightly over the threshold where you're not writing a 10-line script. Actually, in the end, it's probably going to be like 15 lines, but it's just entirely possible that, I don't know, something. So I'm just saying, by all means try, but somewhere around the 2nd or 3rd hour, feel free to quit, right? So just because there's no real good reason to sit there, debugging something. And what you're looking for is you're looking for that quadratic when you see an error curve that goes like this and then accelerates, then you're done. Maybe. You're already seeing that, but there's some other suspicious things in your implementation, right? So, yeah. Okay, everybody cool? Okay. Now we're going to go on to the last section. So actually, we're building a hierarchy. We went from the very low level, right? Low level is linear algebra, right? Interestingly, linear algebra is how you solve quadratic optimization. Equality constrained quadratic minimization problems, right? So linear algebra, you could just call it minimizing. It's effective methods for solving for minimizing convex quadratics subject to linear equality constraints, right? Then you say, well, now I know how. Now I'm showing you a method for minimizing smooth functions subject to equality constraints. Someone says, how do you do that? You go, I approximate the smooth function as a quadratic in 22 steps. That's what I do. And you go, well, then what happens? And you go, well, each step is basically minimizing a quadratic function under equality constraint, which is linear algebra. Everybody following this? Okay, so, all right. Next in the hierarchy is we're going to handle inequality constraints. So that's the next one. It's not as straightforward as equality constraints, but we're gonna add inequality constraints and show how to reduce them to solving a sequence of smooth equality constrained minimization problems. That's the overall program. Okay. So first, let's talk about what we're going to be looking at here. So we're going to solve a problem where all of the functions here are smooth. Okay. Now, by the way, that's already done for you by something like CVX Pi or something like that, because it's compiled to a problem that looks like that, right? So, for example, if I said, minimize the L infinity norm of AX minus B or something like that, right? That does not satisfy. That doesn't work here, right? Oh, subject to X non-negative. The X non-negative works. The objective does not. So you would transform that to an LP, but an LP satisfies this for sure because all the FIs, they're all affine. And affine is, well, really very smooth, right? So, okay, so this is the idea. Now we'll assume that the problem is strictly feasible and, so that's fine. And that means that strong duality holds and there's a dual optimum and all that kind of stuff. Okay, so examples would be things like, LP, QP, QCQP, GP is one. Because GP, all the FIs are log sum exp of an affine thing. That's what a GP is. Okay, here's one, is entropy maximization with linear inequality constraints. So, here would be a fun one. X represents a probability distribution on some finite number of things. This says minimize, this is negative entropy. This says maximize the entropy over all distributions that satisfy linear equality constraints and linear inequality constraints. Now, a linear constraint on a probability vector is actually precisely the same as just an expectation of an event, like period, right? It's the expectation of function, right, on the event space, which is these n things, right? So this would be something like this. You say, well, I have a discrete random variable, and I have a whole bunch of it. I can tell you about the probability that it's in this set, probability in that set. I can give you ranges on those, right? The probability that it's between here and here it's between 0.1 and 0.2 or something like that, right? Anyway, then this says, find me the maximum entropy distribution that satisfies those constraints, right? So, okay. All right. Okay, so I think I already mentioned this sort of stuff. We'll get to things like SDPs and SSEPs. They're actually better handle this problems with generalized inequality. So we'll handle that later. Okay, so everything is going to hinge around this thing called the log barrier. You've seen it before, and we'll talk more about this on Thursday. But the story is actually kind of interesting. That it goes like this, right? You say, I have these constraints and I don't know, I don't know how to handle constraints, right? And a constraint looks like this. If this is fi of x, here's 0, right? And basically there's a function that looks like this, right? And this says, if you're less than or equal to 0, I will assess you a charge of 0. If you're positive, I will assess a charge of plus infinity. right? So this is the semantics of a constraint. This is actually why people call it a hard constraint, okay? What we're going to do here is actually, it's this exact same story as duality, Lagrangian duality. Lagrangian duality, I don't know if you remember, but the story started this way, and then someone said, I'm going to approximate this function. And you go, yeah, go ahead, please. And they say, yeah, here's my approximation, right? I mean, this is the beginning of the story of Lagrangian duality. To which a normal person would say, this is not a particularly good approximation of this, right? I mean, there's no one could say that, right? Now, that story had a happy ending, right? Because it went on, and it turned out for convex things, it turns out if you get these slopes just right, then it actually is a good approximation. Actually, it's an infinitely good approximation, right? Everybody, and then there was a lot of other stuff, like these were the prices and all that kind of stuff. That's fine. Okay. This story actually is way better. This story starts this way, and we'll continue the discussion on Friday. This story starts this way. Someone says, well, I'd like to apply Newton's method, but I have this function that's 0 and then goes up to plus infinity. So it's not continuous, it's not differential, it's not. And so there's a lot of things you could do. One thing you can actually do is just like apply Newton's method to this. How well would that work? Not well, right? In fact, it wouldn't work at all, right? And someone would say, well, it didn't work because you need a smooth function, right? So you'd say, fine, I'll just make a smooth function. I'll make a function that looks like this, right? Maybe roughly, right? It's a barrier function. That's a thing, right? It's smooth, goes to infinity, and so on. I can apply Newton's method to that, right? And so that's actually how we're going to start here. So we'll quit. I think we'll quit for today, and then we'll continue this. Good luck on your implementing your Newton solver.